All right, this is a little bit of a walkthrough of how to do some of these problems. What I would suggest you do is to turn off the video for occasionally and try to work the problems out yourself, and then just kind of speed through them to see what the answer is. So I'm going to talk this one through step by step. So it says a rigid container holds a gas at a pressure of 55 kPa and a temperature of negative 100.0 Celsius. What will the pressure be when the temperature is increased to 200.0 degrees Celsius? So the first thing I'm going to do is I'm going to write down my variables. So my P1 is going to be equal to 55 kPa. My T1 is going to be negative 100.0, and that's in Celsius. My final pressure will be my unknown, and my final temperature is 200.0 Celsius. Well, as I'm looking at this, the first thing I need to do is to convert my temperatures to Kelvin. So I'm going to add 273. When I do that, this is going to be 173 because I've got a negative number there. And I'm going to do the same thing here. So I'm going to add 273. And that's going to give me 473.0. And that's going to be Kelvin, and this is Kelvin. All right, I'm ready to start working this problem. All right, now the formula that I'm going to use for each one of these is the combined gas law. Because when I've got change going on, I can use that combined gas law, and I can just cross off the variables that I don't need. So the combined gas law is P1 times V1 over T1 is equal to P2 V2 over T2. Now in this problem that I'm doing right here, temp or volume is not mentioned in this problem at all, so I don't really need to have that. I can just cross it right off and ignore it. So the next thing I need to do is to rearrange my formula. So I'm going to cross multiply. So there's my first one. It doesn't matter which order you're doing this in. So I'm going to end up with P1 times T2 is equal to, now I'm going to cross multiply the second way. And I'm going to have T1 times P2. Now I'm ready to rearrange this. My unknown is P2, so I'm going to slide that over. So P2 is by itself. So P2 will be equal to P1 times T2 over T1. R2D2 C3PO, lots of numbers there. Now I'm ready to just substitute in the numbers in my problem. P1 was 55 kPa. T2, when I converted it, was 473.0. And my T1, when I converted it, was 173 K. Well, we're not putting the units down, so we'll just go with that. So now I'm ready to put that in my calculator. Let me pause this while So when I put that in the calculator, I'm going to get 150.38, blah, 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 blah. Now I got to check for my significant figures. Because 55 has two significant figures, the rest have three, I need to round this so it has two significant figures. So the final answer is going to be 150, and the unit that I'm going to need for that is the unit of pressure, kPa. And that's my answer for this one. All right, let's go ahead and try another one. Again, if you want to go ahead and stop the video so that you can work this out for yourself and then check your answer. But I'm going to go ahead and talk right through this. So we've got 12.70 liters of gas has a pressure of 0.63 atmospheres. What is the volume, there's my unknown, of the gas at 105 kPa? So I'm going to write down my variables. So V1 is equal to 12.70 liters. My P1, I don't see a temperature, so this is P1, is equal to 0.63 atmospheres. V2 is my unknown, and P2 equals 105 kPa. Now I'm going to look at the units, and I can see that, that unit and this unit do not match. In order to do this problem, I first have to convert this so that they both have the same units. It doesn't matter which way I do this, but I do have to convert this, and this becomes just a small little factor label problem. So I'm going to convert to atmospheres. So I have 105 kPa, there's my known. Now I'm going to need to look at my reference table and find out what is 100 kPa is equal to what. So in order to find out what this is equal to, so I've got kP on the top, 101.3 kPa is atmospheres. So 1.00 atmospheres. Put this in the calculator. I'm going to use my fraction button. And in the top of my fraction, I've got 105 times 1.00. And in the bottom, I've got 101.3. Press enter. And that converts this to 1.0. Now, I want three significant figures. So 1.04 atmospheres. So that is going to be equal to 1.04 atmospheres. Now my units are matching up, so I can go ahead and do the problem. Again, I'm going to go ahead and I'm going to use the combined gas law. P1 times V1 over T1 is equal to P2 V2 over T2 R2D2. Now, I'm looking at my problem. I do not see that I've got any temperature at all, so I can cross that off. My unknown is V2, so I got to have that by itself, which means I can slide that over. And when I convert this and rearrange my formula, I'm going to end up with V2 is equal to P1 times V1 over P2. Now comes the easy part, substituting my numbers in. V2 is going to be equal to, well, my P1 was 0.63 atmospheres. And my V1 was 12.70 liters. And on the bottom there, P2, now I've changed it, so I'm going to use the value that I converted, 1.04 atmospheres. My atmospheres are now canceling out, so they go away. And when I put this in the calculator, it's going to be 0.63 times 12.70, drop down to the bottom, 1.04 equals, and V2 will be equal to 7.6932, blah, 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 blah. I'm going to look to see how many significant figures I need. And that should be a question mark. So here we've got 4 significant figures, here we've got 2, and here we've got 3, so I have to have 2 significant figures in my answer. So V2 will be equal to 7.7. Now, liters is the unit I'm left with after I cross everything out, so the volume is going to be 7.7 liters. Look at my reference table, and I'm going to find standard pressures. Well, these are all equal to each other. Get my thing to stop. It's twisted. That's driving me bananas. Okay, well, we're just going to run with it. So what this means is 1 atmosphere is equal to 14.7 psi, which is equal to 101.3 kPa, and then these are all equal to. So I've got kPa for my problem, so I'm going to need that 101.3. Equal to, now I'm going to find atmospheres, and there it is, 1.00 at my conversion chart over here. And the unit, to find millimeters of mercury, and there it is, millimeters of mercury, and that's going to be my ending pressure reference table. And now I'm looking at standard temperature, which is right here. And I'm going to grab Kelvin because why not? I mean, I don't want to have to convert it again. I might as well use that. So 101.3 kPa is the value I'm going to. So I'm going to work this next problem. What I'd like you guys to do is to pause the video and try it yourself. And I'll work it all out, and then I'll start the video back up when I've got the problem done so you can see my work and you can check your final answer. All right, before I go too much further on this problem, I'm looking at this and I went ahead and I converted the temperature to Kelvin. But then I'm looking at the units here for the volume. Here I've got milliliters and here I have liters. Well, once again, they don't match up, so I got to convert it. So I need to either convert liters to milliliters or milliliters to liters. So this is another little factor label problem. And I kind of scooch this to the side so I can do that. So I think I'm going to go for 2.5 liters and convert that to milliliters. So that's going to be my known. 1 liter, and you can use your other side of your reference table to see this. 1 liter is 1,000 milliliters. So when I put this in the calculator, that's going to be equal to, oops, let me change colors here. 2.5 times 1,000 is going to be 2,500 milliliters. So now I'm ready to do this problem. I'm going to go ahead and stop it so you guys can go ahead and work this problem also. So the final answer you should get is 220 K, because we need to have two significant figures because of our 2.5 liters, which was our original starting or ending volume. All right, same thing. I'm going to go ahead and pause this, work this problem out so you can check your answer. Actually, before I do that, I want to just point out STP. Remember that STP stands for standard temperature and pressure. So I'm going to go ahead and show you how to find the variables for this one. So a gas has a volume of 6,460 milliliters, and we've got 807 millimeters of mercury and a temperature of 77.2 degrees Celsius. What is the volume of the gas in liters at STP? So first thing I'm going to do is I'm going to list my variables. So my V1 is going to be equal to 6,460 milliliters. My P1 is equal to 807 millimeters of mercury. My temperature one is equal to 77.2 degrees Celsius. Now I know I'm going to need to change that, so I'm going to do that right now. So put that in the calculator just to check everything. So 77.2 plus 273 equals, that's going to change that to 350.2 Kelvin. So I've got that all fixed. Now my volume 2 is going to be equal to, I don't know, but it needs to be in liters. My final pressure, it said, was at STP. So what I'm going to do is I'm going to go back. What I'm using here is millimeters of mercury. So I'm just going to write that down. So P2 is equal to 760 millimeters of mercury. My final temperature, T2, is going to be equal to, again, I'm going to go to, so my final temperature is 273.15, or we're just going to use the 273 to make it a little bit less numbers to punch in. I'm okay with you guys using 273 instead of 273.15. So now I'm ready to work this problem. I'm going to stop the video and go ahead and plug it in, and you see if you get the same answer. All right, so let's take a look at this answer kind of step by step. I'll kind of zoom into what I did. So the first thing is that I'm using the combined gas law because I do have all of those variables, and V2 is my unknown. So I go ahead and I do my cross multiply, which gives me this right here. Then I go ahead and isolate my variable, which gives me this version of the formula right here. substitute in my numbers, and solve. Now, when I solve, remember this unit was milliliters. So my answer is in milliliters. It specifically asked for liters. So then what I did is I went ahead and converted that into liters by dividing by 1,000, because there are 1,000 milliliters in 1 liter. And that's your answer to that question. All right, same thing. Going to go ahead and do this problem, and let's see if you get the same answer I do. All right, let's take a look at this problem. So this is one that's not a combined gas law. There's no change going on here. I've got a pressure, I've got a number of moles, I've got a volume, and I have a temperature. So it's going to be a PV equals nRT, or a PIV-NERT problem. So each one of these variables, so obviously I'm solving for pressure. Now my volume, because I'm going to use this R factor, I've got to have liters as my unit. I'm going to use atmospheres as my pressure. I'm going to use, of course, degrees Kelvin, and I've got to have moles. So I'm going to look at each of my variables. So this one started off in milliliters, so I went ahead and I converted that to liters. So now I have it in liters, so it's going to work for my problem. I went ahead and converted my temperature. Now for this one I need to have moles, right? I can't just have grams. So what you do is you're going to convert that to number of moles. So when I convert that, I get 2.18 moles. Remember, you're going to have to figure out the molar mass right here and then put that into your conversion factor. Now I'm ready to rearrange my formula. There it is, rearranged. Substitute in my numbers. Put it in the calculator, and this is the answer you'll get. The pressure is equal to 5.05 atmospheres. And my answer is going to be in atmospheres because the R constant that I used has atmospheres as its pressure unit. My chart here. All right, those are a lot of problems. So what I'm going to do right here is I'm going to do this nice, easy partial pressure problem. So we've got a mixture of gases that has 4 different gases. The total pressure, so the pressure total, is equal to 511.56 kPa. The pressure of the nitrogen is equal to, this is going to be a messy one because we've got different pressure units. 548 millimeters of mercury. The pressure of the oxygen is equal to 196 kPa. And the pressure of the hydrogen is standard pressure. So I can choose standard pressure whatever way I want. So I'm going to convert everything to kPa. So 101.3 kPa is standard pressure. You can look at that right. And I've got one more, and it looks like I have to find the pressure of the fluorine gas. There's my unknown. So, pretty easy problem, but the first thing I got to do is make sure that all these are in the same unit. So this one needs to be converted. So millimeters of mercury, there's 760 millimeters of mercury is equal to 101.3 kPa. So I'm going to go ahead and convert that to kPa. Put it in my calculator, fraction button, 584 times 101.3 on the top, divide it by 760 equals, that's going to give you, and I want 3 significant figures, so that's going to be 77.8 kPa. Now I'm ready for my problem. So my total pressure is 511.56 kPa, which is equal to, actually I'm going to write this down here a little bit lower, just so I have more room. So 511.56 is my total pressure. 77.8 is the pressure of the nitrogen, plus 196 is the pressure of the oxygen, plus 101.3 is the pressure of that hydrogen, plus my unknown. So I'm going to add these numbers together. 77.8 plus 196 plus 101.3 equals. So when you add those together, you get 375.1. I'm going to subtract it from this side, subtract it from this side, and find out what my answer is. So 511.56 minus 375.1 equals, I'm going to need to have one significant figure in my, I need no decimal places in my answer because 196 does not have a decimal place, and this is an addition problem. So I need to round this so that I've got no decimal places. So the answer I get in the calculator is 136.46. So the pressure, so P of the fluorine, is going to end up being 136, and the unit is going to be kPa. No decimal places. All right, I think that's probably good for right now. So there's an example of some of the gas law problems. You've seen a ideal gas law problem, you've seen different versions of a combined gas law problem, and now you've seen a partial pressure problem. The end.